Prasant K. Panigiri from ISET, Kolkata. Professor Panigiri is not new to us. He had already visited Bharathidasan University and lectures a few times. Professor Panigiri possesses a very inspiring CV. He got his PhD from University of Rochester, United States in the year 1988 and continued his postdoctoral studies both in USA and Canada at the University of Illinois and University of Montreal, Canada. He started his academic career in the University of Hyderabad and then shifted to Physical Research Laboratory, Ahmedabad, before settling down at ISET, Kolkata. He is one of the very active researchers in the field of nonlinear dynamics, and his research interests widens in the areas not only in nonlinear dynamics, but also in physics of cold atoms and molecules, quantum computation, and quantum information. He is serving as an editorial board member of several journals. As far as I know, he trained a large number of undergraduate students in quantum computation and information. Several students have completed their PhD under his supervision. I insist the student participants of this seminar should visit his homepage and get acquainted with his research works. With this short introduction, now I invite Professor Panigiri to start his lecture. Over to you, sir.
Thank you. Thank you. I will just now share my little task introduction. Okay, now. Share. Okay, got it. Am I or my screen is visible?
No.
Yeah, already. Yeah.
Screen again.
Just click on that. Oh, okay. Okay. And is it visible?
It's coming, I think. Yeah, it's visible now.
Okay. So you see, I am still scared of online presentation.
Yeah.
You need help with regard to that. Okay. So.
Yeah. Maybe. Yeah.
Okay. So now I will start.
Yeah. If you want, you can change the full screen to full screen mode. Or leave it as it is.
Let me see if it is possible. Okay, so let it be there. Okay, so thank you, Senthil, for your kind introduction. And I must say that for the youngsters who are there, that Trichy has been, one of the my pilgrim sites, which from University of Hyderabad I used to visit every March. And our great inspiration has been Professor Lakshmanan, whose books, whose schools and workshops have been inspirational to all of us, and we do follow his research very closely. And a lot of my works on nonlinear dynamics have been motivated to Professor Lakshmanan's work, and we have learned quite a bit, from him, from the students whom we have trained, including Senthil, this beautiful school which has been started there, and overall this permeating atmosphere of importance of nonlinear dynamics in India. And so therefore I would like to thank again Senthil for inviting me, and this is a very nice opportunity to interact with you people, all young people. And so I will be talking about this supersolid phase in ultracold atoms, and you will see this thing what I am going to talk about. And this I had given a talk in this SM Bose Center, so the same talk I am presenting here because that was for a general audience. And with very minimal, change from nonlinear Schrodinger equation, you can actually show that the same equation which describes Bose-Einstein condensate can describe the so-called supersolid phase. So let me be very brief about this. What is the supersolid? You people must be interested in it. Ultracold atoms, of course, you are familiar. Now we obtained our Bose-Einstein condensate in ultracold atoms in 1995. So now they are all at nanokelvin temperature. You are familiar with gas, liquid, and solid phases. Concentrating on solid phase, what is a solid? Typically, for example, a crystal, you have a potential which is periodic. That leads to in band structure, energy versus momentum. When you look at certain energies are allowed, certain are not allowed. The band structure that arises because of periodic potential. Now, and then there will be vibrations around the equilibrium position where the atoms are arranged. Those are basically phonon modes, and electrons move around in them. Now, when it came to ultracold atoms, we came across this state of matter called condensate, Bose-Einstein condensate. So initially predicted by Einstein by looking at the Bose distribution function and realizing that with a non-zero chemical potential, you have the potential, all the atoms will be occupying one level, the ground state, the condensed phase of matter. That is Bose-Einstein condensate. Originally, liquid helium was envisaged as the system where it occurs, and it occurred there. But the problem was that it was a very strongly interacting system, very difficult to study. So we had to wait until 1995, where it was produced under laboratory conditions in a controlled manner to study all the properties which was predicted, and many things came out of that. You can actually confine it to 3 dimension, 2 dimension, 1 dimension. And if you look at, for example, your professors there, starting from Professor Lakshman, many interesting contributions to this field has come from there. You can easily interact and about Bose-Einstein condensate, many aspects of it you realize from there. The main point is that with such a quantum matter at very low temperature is described by a simple equation, and that equation is nonlinear Schrodinger equation. I'll show you that another predicted phase of matter will come out of the same equation with a slight change, which also has been experimentally verified. Okay, so now outline of the talk. So I'll talk about Bose-Einstein condensate, because from the same system, a slight change, which is required because of both theoretical and experimental requirement, you will be able to see a supersolid phase of matter. Now, as I mentioned to you, that originally it was liquid helium, where Bose-Einstein condensate was realized. Why is it that we faced problem there and then subsequently moved to these controlled ultra-cold systems? I'll point out it's a good lesson. Basically, a strongly interacting gas and so liquid, which created problem. And amazingly, this superfluidity shows a lot of you see the word super. So the heat, starting from heat transport to movement on the surface, many interesting phenomena came out, which finally was ascribed to this superconductivity, superfluidity, the superfluidity in liquid helium. So this was the phase where people could cool down to very low temperature. So this matter, particular metals losing resistance, hence superconductivity, and liquid helium showing superfluidity, very amazing properties. All these things came out because we could cool the matter down to a very low temperature. Now, supersolid phase was another, which around the same time, 50s, I'll show you the brief history of that, was also predicted. Now, again, solid, we are all familiar. Super is the word which I will qualify for you as we proceed. Now, what I'll show you that same system can host very many kind of things. One is something called quantum droplet. Again, all very low temperature, ultra cold systems, very dilute. What is the meaning of dilute? Atom density is very low. And it is the same system, Bose-Einstein condensate, where the atom density is very low, nanokelvin temperature, because of which, interaction is not also very strong. One could approximate it very nicely that this whole equation that describes this phase is a nonlinear Schrodinger equation. Now, in 2015, it was Petrov who pointed out that in real system you have to take into account something called a quantum corrections that can come out if you look at the things more carefully. So this was predicted originally by Yang, Lee, and Huang. So that in 56, that was, and if you put that term, the equation changes minimally, very small change. And that could give rise to something like a droplet. It's something like a nucleus. A nucleus is like a quantum droplet, protons and neutrons are put into a droplet kind of thing. So the word droplet is what you observe in real systems. It is quantum. What is the quantum nature? We'll see as we go along. What I'll show you is that the same system in a different parameter range, you will realize something called a supersolid phase. So main point to emphasize is that the supersolid phase will naturally come out in this Bose-Einstein condensate phase if you take into account this additional correction which was predicted and because of which the so-called quantum droplets exist, and experimental also has found verification. So I hope the same system, people look at it more carefully, people will be able to realize the supersolid phase. It is actually true that supersolid phase has been seen experimentally, but slightly different system. The dipoles, this dipolar BC is where they have seen. So I'll point out to you some of the literature, but what I'm telling is slightly different system. A system where droplets have been observed, but supersolid has not been observed. But the underlying system is very simple, easy to describe. Even any young person, particularly ones coming from teaching, you can sit down and play around and take input from your supervisors and get good results, because a lot of things can be done. Very simple system. Then I'll conclude. Okay. Anywhere you can stop me, and I'm going very slow because it's meant for you people, you younger people, and so I'm going slow. You can stop me at any time. So it was Bose who derived this Bose-Einstein distribution in 1925, sitting in Dhaka. He sent it to Einstein to go through it and possibly translate it to German for communication to a journal. Einstein went through it, and what was the formula? What you have studied in your BSc, that this distribution, the Planck distribution. And note that the denominator. Denominator was exponential e by kt minus 1. So that minus 1 is very crucial. And note e by kt, no mu. So therefore you can say if it is that e exponential e by kt, if it can become 1, then 1 by denominator can have a 0 because of that minus sign. So 1 over, let me add again, distribution function is 1 over e to the power minus e by kt minus 1. So that minus 1 is the crucial factor, that minus sign, that gives us a possibility that there will be like 1 over 0 term, which will be infinity. That is what Einstein realized. But he found that for photon, where mu is equal to 0, chemical potential is equal to 0, this will not be possible. Then, the genius of Einstein realized it's not very difficult to see that there could be atoms which are like Bose particles. The ones which we are seeing in 1995, these alkali atoms. Rubidium, cesium, sodium, all those things are actually bosons. Now, how do you know they are bosons? You can actually see that proton and electron number, they don't matter, because protons have spin half, electrons have spin half. Originally, all the spin halves, they will add up to give you bosons, because half plus half, as you know, is 1 plus 0. Any amount of addition you do, you'll always find integral spin, therefore bosons. So the atoms nature, namely is it boson or fermion, will be described by the neutrons. If there are odd number of neutrons, then it's a fermion. If there are even number of neutrons, then it's a boson. Because for a neutral atom, proton neutrons essentially give rise to a boson. So it's a neutron number which describes it as a fermion or a boson. Einstein immediately realized it, and therefore he predicted that if you look at these kind of systems, because they have a chemical potential, you can easily check. Very simple calculation tells you that the exponential e minus mu by kt, when t tends to 0 and e tending towards mu, it will become 1, therefore it will blow up. So Einstein very nicely separated out the divergence part. Very beautiful derivation. All young people should go through, for example, in the books of your preference. We studied it from Patria, very nice book. And you should see the genius of Einstein, how he separated out that singular part, that there is a blowing up part. That blowing up part is the one which is, your condensate part. Then you may ask, if it is infinity, how do we handle it? So that is where you will see, many things come into picture, something called regularization, how to treat divergence. What Einstein physically realized, the total number of atoms are n. So therefore, that integration, rho integration over the whole phase space will give you the number of atoms, totally gen. So you separate out the divergent part like a delta function, keep the separate part where the zero is not there, and you will find beautiful number theory things come out like zeta 3, zeta function, Riemann zeta function comes out, and that integrated quantity is physical, being controlled by the number of atoms n, which he could separate out into condensate part n0 plus excited part, and it's very simple, physically very intuitive derivation. And all the youngsters should go through it to see how divergence quantities can be handled. It was the first time handled by Einstein. Earlier people, classical domains, there were divergences. But you will soon find out that in physics, we encounter divergences all the time. And particularly when there is phase transition, second order phase transition. So Einstein taught us how to do it. But then it was realized that what Einstein was dealing was with, free atoms, non-interacting atoms, neutral atoms, Bose particles, having even number of neutrons. But it was Bogoliubov who pointed out, 1947, that if you don't have interaction, then there is no condensation. But before that, it was 47. And in 30s, earlier, for example, this Dutch physicist, they have pulled, it was Kapitsa who studied very carefully properties of liquid helium. The liquid helium, in fact, was a condensate, both sides and condensate. But then you try to find out so-called lambda point is where the transition takes place. Roughly, I think 2.7 degree or some Kelvin, very low temperature. So as you cool, you come across new physics. But the equation was very difficult because it was strongly interacting. 2.7 is relatively high temperature. So there was always a normal phase, cold, ultra cold, it was not ultra cold. So it was very difficult to separate out the temperature effect versus this thing. But yet, people used it, studied many properties, found out very interesting properties, which led to the behavior of superfluidity. How this, and of course, it was, for example, from Russia, Kapitsa, then Landau, who pointed and studied these properties, predicted many things. Kapitsa got his Nobel Prize because of that. Landau also had a significant contribution to that. So, but it was these two gentlemen, Gross and Pitavsky, who pointed out that the whole thing can be described in a very simple way, the so-called nonlinear equations. But their motivation was something else, because liquid helium could not be described like it because of it was very quantum in nature. There were quantum fluctuations. Temperature was very high, relatively high. So there was always condensate phase mixed up with the high temperature phase. So but the story goes that Pitavsky was a student of Landau. When he sold it to Landau, it is the mean field equation of for describing both side and condensate. Essentially, Landau, who was a top taskmaster, threw it to the garbage. Pitavsky published it independently. Gross also, around the same time, came up with this idea that, the simple equation, you can see, Schrodinger equation is without this fellow. That's what we study all the time. Now, why it is nonlinear? Because this equation, simplest, equation which is nonlinear and universal applications. You just see, for example, rogue waves from about which a lot of work has been done in 3C. Same equation describing water waves in deep water. For example, look at condensation of this excitons in solid, same equation. Optical fiber, same equation, except H bar has to change. It's so amazing that one simple equation, simplest extension in terms of linearity is lost, describes so many universal phenomena. So probably the most studied equation in physics, apart from Schrodinger equation itself. Now, therefore, here the parameters are quite obvious, that mass, M is mass, and what is this interaction potential? This one, if you see, look at physically, it describes the interaction of particles. This is the equation which comes from a Lagrangian. In the Lagrangian, you will find out that this term gives rise to interaction. How does it look like? It looks like psi star psi times psi star psi. If you have that term in the Lagrangian, if you vary that Lagrangian, you will get a cubic term here. the so-called cubic nonlinearity of the nonlinear solid equation. But in the case of Lagrangian, it comes these two-body interactions, psi star psi, psi star psi. Why is it two-body? Psi star psi is the probability of finding a particle at R. Another psi star psi is the probability of finding the particle at the same point. So therefore, this is operative when two particles meet together. So physically, if you say psi is like an annihilation operator, psi star is like creation operator. So two particles come, meet at some location for R, where finding both of them has a probability of psi star psi times psi star psi. Then they get destroyed and recreated again. So that is the modern field theoretical language of describing this kind of interaction. So physically, there are four fields, psi star psi, psi star psi, which comes from the Lagrangian. Variation of the Lagrangian gives rise to the equation of motion. And psi, if it is annihilation, psi star is creation. So therefore, a particle comes, gets annihilated at location R, another particle is created at the same location, and psi star means two-body interactions. Psi star psi is the probability of finding one body, psi star psi is the probability of finding another fellow, and that in experiment, just if you physically picture, it actually tells you on the average particles are coming, hitting each other. If there is a three-body interaction, which again you will find out, there are quite a lot of work from 3C itself, it will be psi star psi, psi star psi, psi star psi. If three of them are there, that is three-body interaction. Does it appear in Bose-Einstein condensate? Yes. If there is a loss, there is a dominant mechanism of loss is three-body interaction. That is described by quintic nonlinearity. This is cubic and quintic. Both are actually present. The first one is responsible for Bose-Einstein condensate. Next one, the quintic one, is responsible for loss of atoms through three-body interaction. So I am dealing with the simplest system. Therefore, I have not taken that into account. But in realistic cases, you have to do that. What is potential? Of course, in a linear equation, this potential is well understood. Whatever you want to solve, like Coulomb potential, you have to put minus E square by R. But here, these are neutral atoms. What people do is they put in a trap. So in the trap is a harmonic trap. Inside, because without the trap, you cannot pull it. Atoms will escape. So that is what the kind of picture you might have seen. Typically, Bose-Einstein velocity distribution at a finite temperature is described by a Maxwell distribution, Maxwell-Boltzmann distribution, which are like Gaussian functions. Exponential minus E by kt, and you will check that in terms of velocity, that energy is half mv square. So it's like a Gaussian distribution in terms of velocity. You see, velocity distribution. But as you cool it down at very low temperature, nanokelvin temperature, you see this peak goes away. So this is due to the trap. The trap has now put all the particles together at one place. So the distribution, which is very different, and all the atoms are centered and near the origin, because the trap is like a ball, and this is your Bose-Einstein condensate. So distribution changes. So that is what they find out, velocity distribution. This is for radium. Now, of course, these three groups, MIT, and this GILA, they produced in a very controlled way in 1995. And this equation described the properties perfectly. These are the published papers, and very simple, numerically it was solved, three-dimensional thing, and that gave rise to a Nobel Prize in 2001. Now, so three dimension, very difficult to solve. Numerically you have to do, but lower dimension you will find out they are solvable. So now let me directly go to this during around the same time. See, this 56, 57 was a very nice period in physics. Superconductivity was explained by both Bardeen, Cooper, and Schreiber, BCS theory. Then, Fermi gave his model for, quasi-particles, which is essentially used in BCS theory to describe superconductivity. Then you see this, when people are talking about, this, for example, I'll show you the reference of this same person, Jetman Gross, who predicted the supersolid. So that immediately arose the curiosity of Onsager. You young people should read about Onsager, how Gibbs brought him, Gibbs thinking that he's a very experienced physicist, and he had to do very nice papers. And Onsager's statistical mechanics, we read about these theorems in statistical mechanics. essentially when you perturb some system, how it reacts. And then Gibbs, thermodynamics person Gibbs in Yale realized that he's too young, he doesn't have a PhD. So then he told him to do a PhD, otherwise he cannot be observed as a faculty. This man said, I would like to work only on mathematical physics. So he looked at, for example, properties of mathematical functions, these conoidal functions and other kind of things which we people make use of it very extensively in linear equations. So his PhD was on mathematical equations. But then, after that, he stayed in the chemistry department, starting from Ising model to many things. He contributed very significantly. It's worth reading about him. There are very popular things written about him, how he solved the Ising model, how he gave the 2-point function, and many interesting things. So with Penrose, they came up with a theorem forbidding that if you take liquid helium and then try to cool it or do something else, you cannot have a, this supersolid phase. This one is a very nice paper, mathematically very clean, precisely explains to you what is the meaning of a long-range order. You see, long-range configuration order. Then estimates what should be the percentage of atoms in the condensed phase and what would be the things which are at higher temperature, thermal equilibrium. You see 8% of the atoms are condensed. Extremely beautiful paper. And so this paper, and then many very quantitative analysis of that paper, very readable paper. Okay, and it was they pointed out that liquid helium really satisfies the criteria for Bose-Einstein and condensate. And you see this factor, these two factors to remember that in the condensed phase, this exponential kind of thing, average number of atoms per n should go like exponential. Whereas in the normal phase, it should go like order of, some kind of thing. So the exponential and O. Average number of particles in the lowest single particle level. So the exponential occupation is something that defines a Bose-Einstein condensate. And this precisely came from their very systematic analysis, very nice paper, worth reading, many aspects which you can learn quite a bit. So the Gross paper was in 57, where he pointed out about the solid state. I think it was around the same time. These two gentlemen were aware about Gross result, and they also pointed out that in this paper that supersolid phase cannot occur. That I will emphasize a little later. Okay, so now let me talk about liquid helium, because that is where everything started. Now, so this abnormally high thermal conductivity is what was observed in 1938. Then Kapitsa pointed out many very systematic study, low viscosity, and the same Misner who gave rise to Misner effect. All these people are doing in cold systems. So superfluid, superconductivity, they're sort of studying together. Now vertices, for example, quantized vertices, as you might have seen, Feynman, Landau, many of these people pointed out that because of angular momentum quantization, vertices will occur. We have seen vertices in water, but these vertices will be special. There will be quantization. You read Feynman's statistical mechanics book, very nice argument, gives a tentative wave function for it. And you will find out in that wave function, the challenge was to get something called a rotor mode. If you look at the dispersion relation, which I'll show it to you, it has a peak at non-zero k, so-called rotor mode. And it's a very interesting thing. Neither Landau nor Feynman. Landau predicted it. Feynman tried to get the rotor minima, but none of them could get it properly. Only Feynman showed that it is decreasing. And rotor mode plays a very crucial role in supersolidity. So many of these things, which you are seeing here, has actually recent relevance. You can actually learn quite a bit. Many of the papers are readable. And it's a pleasure to note that Professor Srinivasan was from Maryland and was director of ICTP for a while, studied this area, which is an open area of research, quite extensively. You find many of his papers, in this area, very open area of research presently. Now, okay. This in this context, you could see the very many Physics Today articles, and other journals also, which points out because superfluidity, superconductivity has not ceased to amaze us. So you hear particularly these collective modes, how heat propagates, what kind of vibrations could be present. Even now also it's a challenging thing. Supersolid is where we are studying it very extensively now. So this very beautiful article by Donnelly is worth reading. This TISA, who was coming up with this two fluid model to describe this peculiar behavior of heat transport. Okay, he had a good insight that there is a two fluid kind of thing. One is a superfluid, one is this thing, but quantitatively there are some problem. And of course, it was Landau who very caustic way, sort of criticized him, and it's a very this 1941 paper worth reading, that is lambda transition. So he pointed out that the dispersion would be very different. In the initially rotation branch, we start with a gap. To excite it, you need some minimum energy. Without which you cannot excite. Phonon is our sound mode, linear dispersion. Now, so then later on he realized that actually both of them will be combined, and the mode will occur like this, that the energy dispersion will be a single dispersion. It is not that both the fellows can be independently excited. So they have to exist together, and rotation will only manifest after some distance P0. It was Landau's contribution. That it will decrease, that is what was Feynman's contribution with a approximate phenomenological wave function. Read his statistical mechanics book, you will find out. And there was a phase, you see this sharp nature, the second order phase transition, the divergence, the fact that second order phase transition show universality was much later understood in 70s by Wilson, who also got a Nobel Prize. There are many aspects in phase transition which are now also challenging, first order, second order, and things are sometimes mixed. So phase transition is a very fascinating phenomena, and the divergence gave rise to normalization group. So many things started, this Higgs mechanism, Goldstone modes. The collective modes are now called Goldstone modes. Rotation mode is the Goldstone mode. So you might have heard about Goldstone, and those Goldstone modes can have two different origins. I'll emphasize as I go along. So you see, thing to learn is that initially 1941, Landau gave two different things. So he modified it in 1947. A great year. It was Gogolubov who pointed out something in 1947. We got our independence. So then, this modification was given that thing cannot be excited at a finite momentum, at a zero momentum. Here it was like zero momentum. This is like exactly like your, phonon, optical phonon, what we have seen in condensed matter. So that he realized. It cannot be like optical phonon, which we see in a regular solid, because it is a superfluid. It has to be combined. After certain momentum P0, you will be able to excite it. And that is what has found experimental verification. You see the difference here. Claim is here, P0, give some energy, at some delta, you will excite another branch. Two of them will coexist. Now here, no, only one mode. When phonon is there, this phonon is not there. Same delta as is here, except at certain momentum P0, you will be able to excite it. And yet, this thing is still not theoretically understood. Okay, so now, this is a Physics Today 2009. So people, after this criticism and this work of Penrose, who pointed out that there cannot be any superfluid phase, people were sort of given up this thing. But there were this gentleman Chester in Cornell, he revived it. He found out that if you read the paper carefully, these two gentlemen, our Penrose, and in that paper they realized that the atoms have to be confined like a delta function. It has to be, that like a regular solid, you have to, the single particle should behave like a delta function. So if you look at this paper, that this is what he is saying, you read it carefully, that if it's a delta function kind of thing, then there cannot be a supersolid phase. But if it is diffuse, like for example, if a delta function like a Gaussian, then in principle it is allowed. That was the result of Chester. That there is a flaw there, namely there is a escape route. So that's what here the implications of this result are discussed in relation to theories of superfluidity and the nature of quantum crystals. So quantum crystals. Why quantum? Because from superfluid phase, which has a quantum nature, which specifically was pointed out much earlier, that the whole thing has one wave function, which is quantum. So that wave function, if it shows periodicity, that will be a crystal. So it's a quantum crystal, the entire thing is like one crystal. So there is a escape route. In that quantum crystal, the atoms will not be localized like a delta function exactly at a site, they will be diffused. So that argument was pointed out Chester, who revived this field again. So 1970. Of course, at that time, Russians also did a lot of work. I'll give you the references. So initially, people looked at the same system, super helium, claiming that if you take a liquid helium and if you rotate it, you'll be able to see. This was studied theoretically. This Kim has done very extensive work that, this phase diagram is there. If you have the pressure versus temperature, normal liquid, this is the so-called normal solid, then superfluid, which people have seen experimentally. And you see, this normal solid comes at a given pressure. You have to put a pressure, otherwise you can't have a normal solid. Whereas normal liquid and superfluid, of course, will exist, even quote unquote with zero pressure. See this page here. Of course, at zero temperature, which is not possible. So you need some temperature, but some amount of pressure is required. But this supersolid fellow, you see, or even normal solid, they will exist only at finite pressure. Now, a lot of interesting works are going on with this. You put pressure, what happens to the nature of the solid? For example, the hydrogen sulfide has recently shown room temperature superconductivity due to pressure at normal temperature. So note this point. So how would it manifest? If you look at this thing, rotate it, look at the moment of inertia, that should show some abnormal behavior, abnormal drop in rotational inertia because of this, viscosity, sudden decrease in viscosity. So these people looked at it carefully, and they were, during my graduate student days and later on also, people were, constantly talking about this phase and trying to discover it. But unfortunately, all those things were, not very conclusive. But these books you see, particularly the Quantum Theory of Solids, is a very beautiful book, Mir publisher's book. And 1992, the year I started doing my PhD, somehow, because of some reason, I had to read this book because I was trying to use ideas about phase transition from here, and I did not realize the importance of the so-called quantum theory of solids. I thought it was regular solid state physics, but now once I'm working on it, I'm going back. It's a gem of a book, very readable book, thin book. So Andreev and Lipschitz in '69, and Lipschitz in his book, who summarizes his results, they also predicted that there is a escape route, which the no-go theorem of Penrose, and this thing is no longer valid. You can escape it, provided you have a diffusive kind of behavior. And they also pointed out that this diffusive distribution of solid with periodicity has to be combined with a superfluid background. So therefore, imagine that the liquid, which is the superfluid component, on top of it sits lumps of matter, which is like a Gaussian distribution, and there is a periodicity in that matter. So that is what the physical picture of supersolid. So there has to be a non-zero background of superfluid, which establishes the supersolid order. On this non-zero background sits lumps of matter of the same material, distributed not like a delta function, but like a Gaussian kind of distribution, and whole thing is periodic. That is the physical picture of a supersolid. Okay, so now superfluidity and solid behavior, periodicity, very close to. So far, everybody predicted in liquid helium, taking all those parameters, but unfortunately, not very conclusive proof has come out yet. Many papers you can check, for example. But finally, it was in dipole at BEC. It's 2018, conclusive in 2019, around this time, it was observed. So that is where you can actually and observe in, there are 3D, 2D, 1D, the behavior is different. You can actually confine it to any dimension as you want. So now you see, for example, in 2019 Nature paper, and what are they talking about? 3 different ways they observe it. One is looking at the Goldstone modes. Now, what are these Goldstone modes? They are the collective vibrations. So the system is actually a superfluid or not, you can see from the collective vibrations. There is something called second sound, which Bogoliubov had predicted. Now, if that kind of sound exists, that means there is a superfluid there. But vortices, if you find vortices, normal matter vortices cannot exist. So people look for this kind of collective behavior to infer about the presence of a superfluid wave. Now, if there is a solid, you should see phonons. So those are the Goldstone modes. What are the collective modes? Collective vibrations around a minimum. All the ions vibrating gives rise to sound mode. So it's a Goldstone mode. The peculiarity of Goldstone mode is that the energy versus dispersion at k goes to 0, energy has to go to 0. So there are two kinds of Goldstone modes. One comes, they arise because of symmetry breaking. So these concepts you will need probably one more round of blackboard discussions. Now what it means is this. If, for example, look at a magnet. In a magnet, above the Curie temperature, you will find out that there is no magnetism, average magnetization 0. The magnets, in fact, small tiny magnets can point out at any direction, so that the average magnetization is 0. But the system is fully symmetric. What is the meaning of symmetry? Any direction you look, you will find a spin. So no direction in space is special. But the moment you cool below Curie temperature, you find out all the atoms, all the magnets, small magnets will arrange in one direction. So that is how you get your ferromagnetism. Iron. If you put a small magnetic field, or in the presence of Earth's magnetic field, all the atoms will arrange along one direction, and you have a big magnet. And the Heisenberg model, it describes it very nicely. So there is something called order parameter, which is magnetization. Above Curie temperature, it is 0. Below that, it is non-zero. So the symmetry is broken. What symmetry? Once you point along one direction, like Z direction, that direction becomes special. If you rotate along that direction, the system will look symmetric. But any other direction, it will not be like that. So originally, when the magnetization was 0, any direction was same. Any direction, you find out there is no specialty. The symmetry, when it breaks, one direction becomes special. What the result of that? That the symmetry is broken. This concept of spontaneous breaking of symmetry, that the Hamiltonian remains same Heisenberg Hamiltonian describes both the phases. Yet the ground state is different. One case, average of magnetization is 0, which is your paramagnetic phase. Other phase, it is non-zero, which is your ferromagnetic phase. So the same Hamiltonian describes the system. In one case, there are no Goldstone modes, there is no collective modes. Other case, collective modes exist. Why these collective modes? Because once you imagine the magnets are small magnets are pointing along one direction, if you give some energy, like a paddy field, they will all dance together. So this paddy field, what we have seen, when the wind blows, they all very nicely move together. That is the Goldstone mode. If it comes by breaking of space, like symmetry, like translation, these Goldstone modes arise because of breaking of spatial symmetry, like translation, rotation. If it's like internal symmetry, like Bose-Einstein wave function psi, is invariant under psi going to exponential I theta times psi. Lagrangian is invariant. That is called internal symmetry. So rotation, translation, parity, these are examples of space-time symmetry. Rotation and translation are continuous, that is discrete. Whereas the so-called U1 symmetry of electromagnetism and Bose-Einstein wave function psi, the Hamiltonian is invariant under psi goes to exponential I theta times psi, that is called an internal symmetry. So internal symmetry also can break because of which Goldstone modes will arise. These two are different. They may interact, may not interact. Now people are studying these things very carefully because we understand the basic principle behind it. This trapped dipolar superfluid, this group led by Pau in Germany observed this low energy Goldstone modes of a supersolid phase. Solid means that this Photon mode will be there. Now what did they see? Let's read about this test. Direct observation of the low energy Goldstone mode revealed the phase rigidity of the system, phase rigidity superfluid, and proved that droplet arrays are supersolid, arrays of droplet. You see, droplet means what? Droplet means like a Gaussian distribution. array is periodicity. That is what supersolid was searching. Okay. So it was, the behavior was like second superfluid, second sound which Bogoliva pointed out. Okay. That is essentially the liquid which is in between the array, droplet arrays. That is what the physical picture which Chester gave. Okay. So now you see, this is the picture which they are given. Now you see small system. So the atoms are there. You see, very nicely arranged. There are two collective modes. And this is the physical picture of symmetry breaking. That, the only phase can change, density is fixed. So this density is fixed at some background, constant background, that is your superfluid density. You check here, lumps of atoms, but in between there is a superfluid component, it is not zero. So this vibration, there are two different kinds of things. There is a phase vibration. Height is same, distribution is same, phase vibration. That is one Goldstone mode. Okay. And there is amplitude vibration. Amplitude vibration is called Higgs mode. In particular physics, we learn called Higgs mode. So amplitude vibration is massive, phase vibration is massless, because as you change the phase, energy is not going to change. These are the two distinct Goldstone modes they observe. And so a very careful experiment only in 2019. Now, these people observed in a slightly different, the Italian group, ISA Italy, they also observed. They observed in a slightly different way the computation of dipole-dipole and contact interaction. You check this point. There are two different interactions which are competing. Contact interaction and dipole-dipole. What I'll show you is that in another way, also you can actually realize it. It's slightly different, but two interactions must contribute. One is contact interaction, which is our psi star psi, psi star psi. Why contact? Because both the atoms have to come closer, exactly in the same location. Psi star psi, psi star psi at same location R. Okay. So that gave rise to this. Do you see? They also refer to droplets. And you see rotons. They confirmed it through rotons. Because it's a collective mode. If the rotons are there, then only you will see it. All right. So now, another group also, this other group. Now, this is a recent one. This was much like what Kim was trying to see in liquid helium. When you rotate it, then you'll find out that this inertia jumps. So self-bound droplets, that is what was your supersolid. This is this incoherent crystal. And how the phase transition takes place. There was a superfluid, then a supersolid, then droplets separate out incoherently. They add up. That is basically a big droplet bound together. And it is like a regular solid because incoherent crystal, you see there is no coherence between them. So that is how these people observe it. Now, recently, let me show you some more experiments. It's always good to see the experiments because that is what we should tune this house group again. Transient supersolid properties. They studied the properties in an array of dipolar quantum. They have basically two-dimensional system. Now, I was telling you about three-body loss. Three-body loss in the Hamiltonian will be psi star psi, psi star psi, psi star psi. But it comes with a negative sign because it's loss. So interesting thing is that many of the papers are readable. You young people can actually read it because the concepts are not very difficult. Now, that U0, the scattering thing, is parameterized by scattering length. What is scattering length? When one atom comes near each other, you find out effectively what area is exposed to the atom so that the other atom comes, hits it and gets effectively stopped by that area. So 4 pi A0 square is the area which the atom gives to another scattering atom. So this is parameterized by in our quantum mechanics book, scattering length. That is how these people study. By changing scattering length, you see all the three phases they can realize. This is the experiment. For example, first look at this guy. This here, this is the supersolid phase where there is, atoms are there, but there is a periodicity. You see density, there is a periodicity. In between, there is superfluid matter. Then after that, it tries to go through a big chunk of matter together, so-called self-bound quantum droplet, which is in a trap. through this phase. So main point is this, that this is the self-bound matter, whole thing together like a BC. Here there is periodicity, but in between it has to have superfluidity. If it's not there, then it is not a supersolid. And what is the precise parameter range? Scattering length around this value. B0 is the Bohr's atomic radius. Scattering length is the parameter which gives you the scattering. This contact interaction, how strong they are, that U0 is done by this. Experimental people parameterize it this way. So now, same group, this Faust group, 2020, a very recent one. So they have also looked at the density fluctuations. Why density fluctuation? Because collective mode. So this is a very active area of research. Pretty much things are there to do, and very elementary concepts what we read from quantum mechanics, you can still use it to study and predict behavior in this very exciting system. And I can emphasize, people are actually looking at these rotor modes carefully, and the interaction of the rotor modes with other modes. Okay, so now, and many of these experiments are actually done because phase is involved, so very careful observation of phase behavior. You see here, I was talking about this rotor mode. So this, they look at the excitation energy of collective modes. As this mode softens, this is called mode softening. This is the minima when they try to when they see experimentally, and this rotor minimum is where beyond that is a supersolid phase. If you see experimental paper, they will find out, they will be always looking for this K rotor. Do solve it numerically, and around that they look at it very carefully. What is the meaning of carefully looking at it? Because then they release this matter. Once they reach K rotor, they release the matter. And if it is solid, they should see behavior of the solidity here, that arrangement of atoms, periodic arrangement of atoms. And if it is supersolid, something has to be there in between. That is what they look at it carefully. Isolated droplet phase, scattering length, namely strong interaction, more strong interaction, repulsion. You see isolated droplet. Supersolid is exactly in between around this area. There is a background, you see, there is a background here. Okay. This is a very recent paper, 2021, PRX paper. Now, two-dimensional supersolidity. Why two-dimension? Because two-dimension is very special. You see so-called Bickety transition, Brzezinski Kostolich-Thouless space transition. Namely, vertices form, they bound, because of which you get. Now, why they are looking for? You see, now they are looking to produce quantum wires, namely 1D systems. Then quantum planar materials. The whole goal is to study basic physics and also use it for technology. Okay. Now, many new things are also coming out. For example, you can actually see supersolid phase also in optics. And many of these optical systems are described by non-Hermitian systems. So I will not get into it. So if I might have shown that in actually you can see supersolid phase in these kind of systems also. Now, I was talking to you about Brzezinski Kostolich-Thouless space transition, because of which these two gentlemen got Nobel Prize. Now there, this behavior of the collective modes will be different. The first sound is like our regular sound, and the second sound is the one which is observed in case of superfluid, and there is a very interesting interaction between them, which appears in this system. So you can people who are curious, take a look at it. They are very recent papers. Now I'll start with droplet phase. How am I doing with respect to time, Senthil? How much time I have? Hello? Am I audible?
Yeah. You can go 15 or 20 minutes more.
Okay, that's good. So as I told you earlier, the example which I will give you where you can find analytical solutions, exact analytical solutions, is where you have not the dipolar phase, but another phase which was predicted for this droplet. You have already seen droplet there. This droplet is slightly different. It's not exact dipole. So if you take a two-component Bose-Einstein condensate, you can find out that in some very special parameter range, the interaction energy would look like a one-dimensional system, but apart from this repulsive term which I mentioned to you in Bose-Einstein condensate, there will be another term. This term was predicted by D. Wang and Yang quite some time back in 56. Of course, you can realize it experimentally, but in an effective system where you want to see its effect in a very controlled way, you can reproduce the same thing if you take a two-component BC, look at a nice suitable parameter range, and these ones are between the components interaction, the same fellows, two-component BC. Between the two components, you should have attractive interspecies interaction. Intraspecies should be repulsive. So those kind of things you can tune. Experimental people can tune. So this gentleman Petrov and then this beautiful paper in 2016, they take that you take this two-dimensional Bose-Einstein condensate, tune the parameters to this kind of parameter domain, then you'll be able to see this quantum droplet, and you can confine to 2 dimension, 1 dimension, whatever you want. Main reason is this, that the equation that comes is called amended Gross-Petersky equation. Very simple equation. Exactly same thing what we have seen earlier. The repulsive two-body interaction giving rise to nonlinearity, cubic nonlinearity, well studied in Bose-Einstein condensate. This is the new term. Here, this term is coming by manipulating our, two-component BC to produce this term. But it was predicted independently by Li, Huang, and Yang, LHY quantum correction in 56. So, in physical systems also they can manifest as this kind of quantum corrections if you look at it carefully, or you can take a two-component BC, manipulate the parameter domain to produce the same kind of physics. So, main thing is see very minimal change to the original equation, repulsion, the attraction. This is only true in 1 dimension. If you go to 3D, you will find out the system will behave differently. 2D, it will behave differently. So that is when you take into account Li, Huang, Yang correction. But in 1D, it is repulsive here, attractive here. You can create this 1D matter in a trap, and you can study the behavior. So because of the simplicity of the model, they attracted our attention. Now, okay. So this is the physical description of Petrov, that under what kind of conditions you can produce it. So he very pictorially points out this is repulsion because they go away from each other. They hit each other, then they try to move away. This is single species Bose-Einstein condensate. Because of repulsion, they are moving away. But amazingly, only when they are moving away, that would lead to corrections. But in two-component Bose-Einstein condensate, you can have repulsion between the species. For example, red is one species, blue is another one. Between them, there has to be repulsion. But, between them, there has to be attraction. And in a given species, there is repulsion. So there is a competition. In that kind of thing, there will be very nice ordering will come. That is the droplet which was pictorially explained in this physics article after Petrov's prediction and experimental verification. So two-component BC, attractive mean field and repulsive beyond mean field corrections. So now you may say that I am giving you opposite sign here. My sign was that, you see, I gave you here, this sign was repulsive attractive. Then why are they talking about in that physics article opposite? Because this is in 3 dimensions. So this actually I was, in the beginning when I read it, I was very confused. I said, what is going on? Then if you go through it, this is a very peculiar system. In 3D, one kind of behavior, where it is produced. In 1D, in a trap, it's very different behavior. So in 3D, attractive mean field, repulsive beyond mean field. Whereas in 1D, it is exactly opposite. The reason for that you can check out. Very nice recent review article by Malomed, which points out this thing. Okay. Now this phase diagram was studied by the gentleman, and people have seen it experimentally. That in fact you can actually produce, for example, if it is this quantum droplet, it should behave like this. There's a flattening here, almost flat kind of thing. That is what characterizes. Now, how do you go from here to here? What are the parameter domains? You can check these papers, very readable papers. This Physics Today article which I mentioned to you. So it's the density distribution which tells you that if it is like this, almost flat, not Gaussian, that is your droplet. Now phase diagrams of ultra dilute droplet. This was Petrov and AstraZeneca they had given. After that, there have been many studies. So now, interesting thing is that self-trapping. Even if there is no trap, you will be able to see it. And that's what they have seen. That the whole thing becomes a weakly bound, atoms, and no trap. If you remove the trap, you can still produce. And this what flat top. That flat top is the one which is different, makes it different from regular. This fact, that top is extremely flat. Okay, so now very good. So now what do we do? Now you can actually check that very same system can produce a supersolid behavior. And interesting thing is that analytically you can solve it. So this paper which you can look at it, but at this moment just see the simple idea. What we did is that what kind of solutions. When you go to look at it in one dimension, you can actually find exact solutions. In fact, this Professor Lakshmanan's group is one of the key players internationally in this area. Starting from books to review articles to conferences, optical fibers, variety of systems which appear, rogue waves, is to you name it, where this equation appears. It has solitons, multi-solitons, varieties of systems, very extensively studied by groups, and dominant contributions coming from TC. Now, okay, so for example, I am looking at a very specific kind of system. This system has solutions which are given by Mobius transform. Simplest one, when, for example, you can check the regular sine cosine functions describe periodic systems. Here, because of the nonlinearity, there is a general function called Sn function. Very interesting function, elliptic functions. M goes to 0, this probably becomes sine. M is equal to 1, this so-called modulus parameter is equal to 1, this probably becomes tan hyperbolic. So here is a function which is solution of a elliptic function, elliptic equation, and they interpolate between sine, cosine, and tan and sec. So there are three of them, Sn, Cn, and Dn. So I am talking about Sn here, you can as well take Cn. So the point is that this parameter M, which is called modulus parameter, if it is absent, this will become sine, solutions of linear equation. When it is present, M is equal to non-zero, at best it can 1, this is solution of a nonlinear equation. And I am trying to solve a nonlinear equation here. It is not linear. Two kinds of nonlinearity. One is cubic nonlinearity, one is quadratic nonlinearity. Cubic nonlinearity is repulsive, coming due to boson particles repelling each other. This flow is attractive, calling because of beyond mean field corrections. Now, I would like to, then the point is that you just substitute it. These functions have specific properties. They, in fact, will be solutions of this. That's what we have shown. So why did we look at, for example, solutions of this kind? You need to have a background. If the background is there, then there is a superfluid background. You need a periodic functions, because the periodic functions gives rise to solid behavior. And the flow is moving, that's the reason V. And this data is called healing length. How big is that correlation length? How far they are correlated to each other? So this is exactly the kind of thing Chester was pointing out. There's a background superfluid, periodic solutions, and they are not like delta function. They're distributed, the kind of thing which you saw in the physics today picture, and we expect the system to be a super fluid plus something else. That something else is this. You can check if this flow is not there, background is not there. That was an amazing thing which which surprised me. Without this thing, this is not there. So in the same phase which gives rise to droplet because of this term, you'll be able to see it if you look at it parameter domain very carefully. Now you just substitute it and you will find that this term plays a very crucial role. In fact, background is 1/3 of that. If this term is not there, then supersolid is not there. So you need that D1 correction, otherwise it's just pairing BC, boson and condensate. Now, one other thing we observed, there are certain non-analytic behavior which comes here. which is expected because from solid to other behavior, it's like a phase function. You can check that when m tends to 0, namely it behaves like a sine function, which we expect for a periodic thing, there should be no amplitude. This is not a solution. So you cannot smoothly go from here to a regular kind of things. Okay, and you see amplitude always is lower than the background. So this also you find, and healing length also is there. Now density is finite, you can check from here. So these are the things which analytically comes out. The good thing is that in 1D kind of model, many things you can solve analytically. And a nice thing is experimental people can check it. In this case, so far no, but in principle they can check it. We are in touch, in fact, with. So main thing is how did you want overcome these objections of on Sagar? There's a background, which is A. Then this thing is like a lump of matter, which is described by SNCN kind of functions, not like a delta function. Now, the interaction plays a very crucial role because without that, there is no background. So this is how these things conspire to give rise to a supersolid phase. Now, more general solutions you can find. In fact, you do find that there is a different parameter domain these solutions occur. Now, furthermore, the chemical potential for droplet and this flow also starts from the same range but different parameter domain. There are varieties of solutions, and why I am listing this one, because you see this is A divided by something. If it is just sine function, it should be linear system. But amazingly, A divided by this, A 1 by 1 plus D sine, with the same sine, sinusoidal function, you can find solutions of a nonlinear equations. This part also I learned from one of the talks of Professor Lakshmanan, where he had looked at a nonlinear systems where these kind of solutions were there. They also appear here. Okay, so physical picture, there is a distribution of atoms, superfluid atoms in between, lump of matter, what they seen experimentally. So, and more general solutions are here. I will not get into them. You can compute energy versus momentum. Then you find that there are other kind of states like kink-like solitons. What are these kink? They are like tan hyperbolic. For example, in case of optical fibers or Bose-Einstein condensate, these are called dark solitons. Okay, so here also you find, but amazingly here again there has to be a background. Without background, so this beyond mean field correction plays a very crucial role. It changes the nature of the solutions from nonlinear solid equation to the system very drastically. So this is kink anti-kink behavior, but very different from optical fibers and BEC. So that also you find analytically the solution. This paper also has coming out, has been accepted. It's coming out. So the behavior is emphasized here. This flat top nature is there. You see, for both of them, flat top kind of behavior comes. In fact, you can combine this kink and anti-kink to produce another, liquid droplet kind of thing. So let me not get into the dispersion relations. You can compute. Okay. Now this BKT transition I was mentioning to you, you can in fact observe the breathing mode kind. It's a new thing which we have predicted, which people have seen not the breathing mode, but regular sound mode. But hopefully somebody might be able to see it. Okay. So now as I told you that photon condensate in principle can show it. And experimentally, a photon condensate has been observed in a confined gas of photons, which is very interesting experimental paper which came out a couple of years back, that you can actually take some chemical, put it in a inside a cylinder kind of thing. This it will emit and absorb photons, so the photons will come to chemical equilibrium, and at a temperature T, that system can show superfluidity of photons. It was experimental observation. What we pointed out that in the same phase, if you slightly make it a two-dimensional system, try to confine and make it quasi one-dimensional, then you will be able to see this kind of behavior, supersolid behavior. Now, what happens is that the same system with two-dimensional photon condensate behaves like nonlinear Schrodinger equation with a source. You see, nonlinear Schrodinger equation with a source, and this actually can derive, give rise to a supersolid phase of photons. So superfluidity has been seen. Hopefully, somebody will do it. And amazing things at room temperature. The whole thing is at room temperature. So I will not get into parameter domain, but in another class of solutions I have listed here, this is so-called Cn function. So please keep in mind Cn, Sn, Dn, and general nature of the solution. They are like Mobius transform, A plus B some function divided by 1 plus D some function. Mobius transform or the fractional linear transform has a very key role in many aspects of science, particularly nonlinear systems. So Sn, Cn, Dn function and Mobius transform that allows you to play around with nonlinear equations very effectively. So some more predictions we have done. Hopefully, these photons, this has not been seen experimentally. So I will not get into details, but superfluid density, so peculiar behavior in a controlled way, you can actually control it. So let me conclude. Now exact superfluid solutions, solid solutions you can find in 1D. Interesting thing to observe is that you should have something more than Bose-Einstein and condensate, these so-called nonlinear interactions, which is described by nonlinear solid equation. There has to be something more. That something more could be in the form of dipole interaction, or it could be in the form of D Huang-Yang correction. D Huang-Yang correction, which is beyond mean field correction, will come in a physical system, or it may come in a two-dimensional, two-component B size, Bose-Einstein condensate, under some specific restrictions. So the droplet phase has been predicted. What we are pointing out in a slightly different parameter domain, you'll be able to see supersolid phase. Kink-like solutions have been seen, but very different from the one which we observed in Bose-Einstein condensate. Now, similarly, the photons also show in a dye field, basically chemical field optical cavity. Experimentally, people have shown at room temperature superfluidity of photons. So what we predict is that in the same system in a two-dimension, in a controlled way, you can actually realize supersolid behavior. And good thing would be it would be in regular, room temperature. So as you know, superconductivity, superfluidity has given tremendous amount of control over sensitivity and many applications. We hope that particularly this photon supersolid or superfluid, which are room temperature, people will play around and in a dye field optical cavity, and this whole system can be realized. And particularly in a country like India, one should be able to realize it because it's a room temperature. These are very recent experiments. Many of these things may be able to find experimental things, verification, and I hope some technological applications also. So I will actually, let me just complete this one, some references. This was done with Aradhya, who is now a faculty in UP, in Mathura, and was a postdoc with me, and many collaborators, for example, Vivek, who is currently in Triple-IT Vadodara, and Niraj is a PhD student. Mithilas has gone to Hong Kong. They're all done during this COVID period. Dhirendra is a PhD student. Gargi, project student from Amity. These are all students from here. Our own ISA student. All during this COVID period, people are shut down and we are working. And I will stop here. So thank you for inviting me, and thanks. I'm open for questions.
Yeah. It's time for questions. Yeah, if you have some doubts, you can raise now.
Yeah, you can ask actually. Yeah.
Hello. Good evening, sir.
Thank you, Prashanta, for a very exciting, fascinating lecture. So I really enjoyed your lecture.
Thank
So
you.
have you looked at the stability properties of these exact quantum droplet solitons?
Actually, not very rigorously. MI has been studied, modulation and stability has been studied.
Yeah.
But within the presence of solitons or even supersolid phase, people have not looked at this carefully.
Okay.
Not yet.
Yeah. At least you can try to look at the linear stability of them. And
I will. Malumed has done some recent work. I'll check it up. There's a review article, but I'll look at it. Thank you.
yeah. And So in higher dimension, I mean, I suppose only numerical results are available.
That is right. That is right. Yeah.
And these numerical solutions show the existence of localized structures, or what kind of?
They show this background superfluid with some Gaussian kind of answers that gives rise to the stable configuration. That they give as answers and look at the evolution through evolution stability.
Yeah. And then in this one dimension, probably beyond this kink like soliton, probably higher order solitons probably have not been found.
No, they have not. They have not been studied. No.
Found exactly. Yeah. No. So there are a lot of things to do. So
Indeed.
Yeah. I hope you can further. Okay. Thanks a lot.
Thank you.
Yeah. Tamilarsan, you can raise your doubt. Raghav.
Sir, sorry, sir. Wrongly touched, sir.
Okay. Raghav, do you have some doubt?
Yes, sir. Good evening, sir. So I have two questions. The first question is regarding the non-Hermitian Hamiltonian. Can we have real solutions or even unitary evolution in non-Hermitian Hamiltonian, sir?
That's a good question. That, in fact, okay, I see there are these two different phases. One phase is, Hamiltonian is non-Hermitian, but the ground state, has real energy. So there you can actually define a norm. Namely, you can define the magnitude. So effectively, you can actually define a evolution which behaves like unitary, but it's not unitary. But because of the norm, it will be very close to like unitary evolution. But in fact, in the other phase where the symmetry, PT symmetry is broken, so there actually not much I can say because norm is not known. Evolution is there, but it's certainly not unitary. In fact, it's a good question. People are actually looking at it carefully. Lot of experimental results. In fact, Professor Laksana has also quite a bit of results there. Senthil also has doing some works there also.
Thank you, sir. Thank you so much. And my second question is regarding this LHY correction.
Yeah.
We know that like LHY correction is beyond mean field. So is it possible that can we go beyond LHY or can we think beyond LHY?
In fact, that's a very good question. Take a look at, for example, my postdoc recently showed me on a review article, 2021, 21 review articles by Malomel and company. They actually look at it very carefully. Take a look at that paper, the review article.
Okay.
Yeah.
Kanna, do you have some questions?
Thank you, Professor Prasanta, for a nice talk.
Thank you, Kanna.
Thank you. So we have dark solitons, which are dark soliton breathers in the background, oscillating dark solitons in the background. Do they have any connection with your solid phase solutions?
Oh, that's again a very beautiful question because breathers are also periodic, right?
Yes.
In fact, that is a good question because there would be definitely breather analog here. That is something which I would like to, maybe we can look at it carefully. Like Professor Lakshman pointed out, many things are unsolved. That would be a good thing to look at. Analog of breathers here.
Okay.
Yeah.
Okay, thank you.
Thank you. Yeah.
So, other questions? Let me check the chat box. No, the chat box, no questions. So if there are no more questions, let me conclude the session by thanking Professor Prasant Panigiri for giving a very illuminating talk. He gave this lecture despite of his busy personal commitments, and he covered almost, all the historical aspects in this particular topic. And he has also shown the applications of nonlinear dynamics in condensed matter physics. Okay. So It's a really enjoyable talk, Professor.
Thank you.
Once again, I thank you for giving your time to us.
And I must really thank to all of you, because Trichy is like, I used to go there every March. It is all, place where I have learned a good amount of nonlinear dynamics. I'm really happy that, it's an opportunity I got from you people. Thank you so
Once this is over, I invite you to Bharathasan University.
much. Yeah.
I will write to you.